In the previous lecture on force and energy, we saw how a force is obtained from the corresponding potential energy by taking its gradient. In this lecture, we explore this little further and then go on to discuss non-conservative forces. As a real life example of calculating the force from a potential, let us now look at the electric field and the potential, or equivalently the potential energy and the force on a charge in an electric dipole. So, I am going to consider a dipole sitting at the origin with charge minus q on the negative x axis and charge plus q on the positive side of the x axis, with the distance between them being 2a. I want to find the electric field at a general point r from the origin. I will do so by taking superposition of fields due to charge minus q, charge plus q, adding and then taking the limit a going to 0. So that limit is taken in such a manner that p equals 2 q a remains unchanged. That defines for me a point dipole sitting at the origin. So, I could either find the field at r by superposition of field due to minus q at r plus field due to plus q at r and get my answer. An easier way, and this will tell you how talking about potential helps at times, could be that I find the potential energy of a unit charge at point r and take its gradient. Negative of that will give me force on that unit charge, which by definition is the electric field at r. Let us do this as an exercise. So, to recap, I have a dipole sitting here. I want to find the field at distance r, which is x from the origin and y this way. The finding potential in this case is easier because I am not doing a vector sum. So, therefore, potential energy for a unit charge q equals 1 at r, the r is given in 2-dimensional space as this x and y point, is going to be potential due to the first charge plus the potential due to the second charge. It is going to be k q over square root of x minus a square plus y square minus, due to the other charge, this one, k q over square root of x plus a square plus y square, where I just want to remind you this distance between the charges is 2a and k is 1 over 4 pi epsilon 0. I am not so much concerned about these quantities, more about taking gradient of this. Since a is very small, so far away from the dipole, I can write 1 over square root of x minus a square plus y square as 1 over square root of x square plus y square minus 2 ax plus a square, and I am going to neglect this term because a, finally I am going to take the limit going to 0 and keep only q times a term. So, I neglect that, making the figure again. I am trying to find the potential due to a dipole at a faraway point, which is x from the origin this way, y this way, this is q minus q, and I made the approximation that 1 over the square root of x minus a square plus y square is equal to 1 over square root of x square approximately plus y square minus 2 a x, which I can write as 1 over square root of r square minus 2 a x, which is approximately equal to 1 over r 1 plus a x over r square. Similarly, I can write 1 over square root of x plus a square plus y square approximately as 1 over r 1 minus a x over r square. Combining the two, I get the potential for this dipole separated by 2a minus q plus q as u at r, where r is this point, distance y, distance x from the origin, as k q over r 1 plus a x over r square. I am working under those approximations where a is very small, minus k q over r 1 minus a x over r square, and that gives me u r to be 2 k q a x over r cubed. Now, when I take the limit a going to 0, such that 2 q a remains constant equal to the dipole moment that I want to have. So, then in that limit this becomes 2 q a gives me the dipole moment k p x over r cubed. You can check that the dimensions are all right. P is q times the distance, this is distance divided by distance cube. So, this is the potential. Now, I want to find the electric field due to this dipole at point r. So, I am finding, so there is a dipole here of magnitude p pointing in x direction. Okay, so, let me now make this dipole I am making slightly big, is in x direction, its magnitude is p, and I am trying to find the electric field at this point r distance away, which is x this way and y this way. I found that u of r for a single charge, so is the potential is equal to k p x over r cubed. So, I can find the x and y components of the force or the electric field, because electric field is the same as force on a unit charge, is equal to f x is equal to minus du dx, which is equal to minus d over dx. I am taking a partial derivative. So, when I do that, y remains a constant of k p x over x square plus y square raised to 3/2. And when I do that, I find, I differentiate this first, I will get 3 over 2, this minus sign goes with that, k p x over x square plus y square raised to 5/2 times 2 x minus k p, I differentiate x. So, I get divided by x square plus y square raised to 3/2. This 2 cancels, so that the expression for the electric field x component that I get is going to be x, which I took to be the partial derivative of u with respect to x, comes out to be 3 k p x square divided by r raised to 5 minus k p over r cubed. Let me see if it is correct. Going back to the previous slide, is 3 k p x square over r raised to 5 minus k p over r cubed. Similarly, I can find E y, which is minus partial of u with respect to y, and this comes out to be minus partial of u with respect to y k p x over x square plus y square raised to 3 halves, and that gives you 3 k p x y over r raised to 5. These are the two components of the electric field. You can check for yourself that this is consistent with the general expression of the electric field, which is given as 1 over r cubed, or rather k over r cubed p dot unit vector in r direction times 3 r minus p. Getting this directly by superimposing the fields due to two charges would be slightly more difficult. So, you see that taking gradient of the potential, which is slightly easier to find, is an effective way of finding the field. Having talked about all these quantities, you may be now wondering what happens to the minimum maximum of the potential in 3-dimensional cases. In 1D cases, I knew that the force was 0 when du dx was 0. If d2u dx square was greater than 0, then I had a minimum of the potential, and similarly d2u dx square less than 0 gave me maximum of the potential, and we have talked in the past, this gave me an equilibrium point or I should say a stable equilibrium point. If I moved a body from this point, it will come back, and this gave me an unstable equilibrium. Point. The body had force 0, but if I moved it away from there, it will just take off, it will not come back. What about in 3D cases? In 3D cases, I am talking about a 3-dimensional force, which is the gradient of u. Of course, if gradient of u is 0, it implies that the force is also going to be 0. But as far as the minimum, maximum and such things are concerned, these are slightly more complicated in 3D cases. For example, although a point could be where the gradient is 0, it does not mean whether that it will be a maximum or a minimum for sure in 3 dimensions. For example, if I come along the x line, suppose at the origin the gradient is 0. If I come along the x line, x axis, u could go through a maximum. On the other hand, you could have a minimum along the y direction. So, to find the minimum maximum in 3D cases, one really has to see, for example, for a minimum, whether in all directions that point the u is minimum. For a maximum, whether coming from all directions that point is a maximum. There could be more complicated cases, as I just discussed. Coming in one direction, it could be a maximum, and the other could be a minimum, which is known as a saddle point. You will learn about these things more in your electrodynamics course. I thought I would just give you a gist of it. Now, let us talk about an issue that we have been avoiding so far, conservative forces and non-conservative forces. How to deal with non-conservative forces? This we have already dealt with. To work with non-conservative forces, we said earlier I should not be able to define a potential energy since the work depends on the path. My simplest example in one dimension is frictional force. More you move, more work you do. You come back to the same point, the work done is not zero, and therefore you cannot define a potential energy for a frictional force in one dimension. How about in three-dimensional case? Let us take two examples and learn through examples. Let's take two forces, F equals xi plus yj, and try to construct potential energies for these, and this equals minus yi plus xj. So I am taking two forces. Let me just draw a line here. F equals xi plus yj and F equals minus yi plus xj. In this case, you see that the force lines are going radially outward. If you don't see it directly, write F as x is r cosine theta, y is r sine theta, so I can write this as cosine theta I plus sine theta j, and by now having learned polar coordinates, this is nothing but r in the radial direction. On the other hand, in this case, the force line are going to be in theta direction at all points. So they are going to look like this. Again, if you don't see them clearly, write this in polar coordinates and you will see that this is nothing but r minus sine theta I plus cosine of theta j, which is nothing but r in theta direction. So farther out you go, the force magnitude increases with respect to r and its direction is in theta direction. Let us try to find the potential energy for the two cases. Again, let me draw a line. F equals xi plus yj, which is minus partial of u with respect to x I minus partial of u with respect to y j, and this implies partial of u with respect to x is equal to minus x, or u could be equal to minus x square plus some function of y, and therefore du dy is equal to df dy is equal to minus y, and this after integration implies that u is equal to minus x square minus y square plus some constant of integration c. Let us try to do the same thing for f equals minus y I plus x j. So partial of u with respect to x is equal to minus y, and I can therefore write u as minus y x plus some function of y, and partial of u with respect to y therefore is going to be equal to minus x plus some df dy, which is strictly a function of y, but du dy cannot be minus x because du dy is given to be plus x, and therefore u cannot be defined. This is a conservative force, this is a non-conservative force. Let me give the same, carry the arguments further. So in the case of f equals xi plus yj, I found that u is equal to minus x square minus y square plus c, I can take as a reference point u at 0, 0 to be 0, then the c becomes 0 and the constant energy surfaces are like this. U becomes more and more negative as you go further and further out, and therefore the force is in this direction, as we can already see, it's radially out. On the other hand, when I take f to be minus yi plus x j, I can't really find a function that will give me gradient of u to be equal to minus f. Another way of looking at it is, you see, from du dx equals minus y, I find u should be of the form of minus xy. On the other hand, if I look at du dy to be equal to x, I find u to be of the form of xy. Both cannot be true. So this is a non-conservative force. I can't really get any potential for this. Now the question we ask, do I always have to try to find the potential energy, and if I can't find it, then I say it's non-conservative, or is there any easier way to look at it? If I all the time I have to integrate the force, it becomes a difficult task. It so happens that there happens to be a differential way of doing the same thing, and now I'd like to talk about that. It also gives me the definition of a quantity called curl. So go back to the definition, restricting myself to 2 dimensions, and the generalization to 3 dimensions is quite easy. I go from point 1 to point 2, and if I find that the work done is independent of which 2 paths I choose, is going to be a conservative force. If it is not independent, or it depends on the path which I choose, then it's going to be a non-conservative force. Also, put another way, if I go from point 1, go around this path and come back to the same point, if the work done is 0, then it is a conservative force. If it is non-zero, then it's not a conservative force. So let us try to do that. Let me go from point x, y to point 2, which is x plus delta x, y plus delta y, and without any loss of generality, let me take this path to be 1a, 1b. Let me take this path to be 2a, 2b. So work along path 1a. Since I am moving along the x axis, this is path 1a, is going to be f x at x y times delta x plus some correction, because f x itself might change. I am going to go all the way to second order. So some correction, let's call it delta f as f x changes along the x axis, delta x square, and some constant k. Okay, this is going to cancel, so I am just putting some constant k. K could be 1/2 or something. As I move along path 1b, that is from here to here, only thing that is changed is y. So this is going to be f of y at x plus delta x, y has not changed, plus some correction, let us call it k1, k2, as I move along y, fy may change, delta y square. I am going to, there should be a delta y here, because that's the distance. So let me expand this. So I get delta w along 1a is equal to f x x y delta x plus some constant k1 partial of x delta x square is going to be fx at fy at x plus delta x, y delta y plus some k2 df y dy delta y square. If I expand this further, I get f y at x and y delta y plus delta f partial of y component of f with respect to x. It changes since I moved by delta x, delta y by Taylor series expansion plus the second order term k2 y square. So, I am keeping all the terms to second order and there could be some higher order term. Let me remind you again, I am calculating this work in going from point 1 to point 2 along path 1a and 1b. I could do similar exercise while going from path 2a and 2b. I can go like this. You can take similar steps and I leave this as an exercise, and you would find that the work done when I go from along this path comes out to be along 2a comes out to be f y at x y delta y plus you can write k2 delta f y del y square, and along 2b, this is 2a, this is 2b, it comes out to be f x at x y delta x plus partial of f x with respect to y delta x delta y plus k1 partial of x with respect to x delta x square plus higher order terms. So, let me flash the previous expressions again. This is delta w 1a 1b expanded, it looks like this. Let us flash back, and you see when I did the work along path 1, I got these contributions, and when I worked along path 2, I got these contributions. Comparing, you will see that this term appears in this case. Similarly, this term and this term, I will remove this, I will focus only on this term and this term appears in this case also. This term appears and this term appears. Only terms that I am left with are this and this. So, if I were to take the difference moving along path 1a and 1 and path 2, I will find that work done along path 1 minus work done along path 2, which is delta w 1 a plus delta w 1 b minus delta w 2 a minus delta w 2 b, and let me flash those things back again. This was delta w 1 a, this was delta w 1 b, these terms cancelled. Similarly, in this case this was delta w 2 a, delta w 2 b, the only terms which are left were these. This also cancelled, and therefore, I get this to be equal to partial of f y with respect to x minus partial of f x with respect to y delta x delta y. If this were to be 0, that is, if force is conservative, then this term must be 0. This implies partial of f y with respect to x minus partial of f x with respect to y must be 0, otherwise not. So, I get delta W1 minus delta W2 is equal to partial of f y with respect to x minus partial of f x with respect to y delta x delta y, and this delta W1 minus delta W2 is nothing but this is the delta W1 is the work done in moving from this point to this point, and minus delta W1 is the work done in moving back along path 2. So, this is the work done in moving the entire closed path, and if this is non-zero, then the force is non-conservative. I can give similar arguments for other dimensions, movement along the plane of y z or movement along the plane of x z, and I find in general that if delta f y over delta x minus delta f x over delta y or delta f z over delta y partial y minus partial y over partial z, or let me write it here, partial f x with respect to z minus partial of f z with respect to x. If they are any one of these is non-zero, you have a non-conservative force. If these are all 0, you have a conservative force. Is there a compact way of writing this? The answer is yes. These are all components of a vector formed by this, which is known as curl of f, and you can see this I, j, k, this is by definition f x, f y, f z, determinant. This gives me all three components that I wrote in the previous slide. This is the z component, this is the x component, this is the y component of that curl that I wrote here. If any of these components is non-zero, force is non-conservative. If they are all 0, the force is conservative. So, I found given a force, I don't really have to calculate the potential energy. I can straight away take its curl. If it is non-zero, non-conservative force; if it is 0, conservative force. This also tells you that, by the way, that curl of a gradient must be 0, because if I define a gradient, that means I am talking about a conservative force. What does this curl mean? Can I get more feeling for it? The answer is yes. As the name suggests, curl is something that describes a curly sort of thing. Let's again go back to our two examples. F equals xi plus yj and f equals minus yi plus xj, and take the curl. Curl is going to be I, j, k, partial with respect to x, partial with respect to y, partial with respect to z of x, y and z, and you can see this is 0. This is 0 here. On the other hand, if I look at the curl of the other example, j, k, partial of x, partial of y, partial of z, this is minus y, x, 0. You will see that it gives a k component or z component which is equal to 2. So, this is non-zero. Let me again make how these force fields were looking. So, F equals x I plus y j, the force was looking something like this, and in this case F equals minus y I plus x j, the force field was looking something like this. In this case, curl of F is equal to 0. In this case, curl of F is not equal to 0. So, this quantity curl seems to give you a non-zero value when things seem to be moving around in circles, or they are curling, they are turning around. On the other hand, if they don't, they go in straight line, curl is 0. You can see in this case very easily, if I take a particle and go around in a circle, work done is going to be non-zero. So, it is a non-conservative force, this is a conservative force. To get more feeling for this, let us look at some more examples. Let us take a force field F, I will just make pictures, which is something like this. As you go out, it increases. As you go on the negative side, it again increases. Let us take another one. As you go up, it increases. As you go down, it increases but in the same direction. You can see if I take a particle around here like this, I do positive work when I go this way, no work, same positive work, and come back here, I have gathered some work. Work done in going around in a closed path is non-zero. That means curl of F is not equal to 0. Similarly here, if I go around the origin in symmetric way, you will see I pick up some positive work, 0 work, negative work equal to this positive work, and 0 again. So, around the origin, the work done seems to be 0. But if I take a closed path here, I do some work here, 0 work, less work because the force has become less, and come back here. So, I have picked up some work in going around a circle. So, on this point, curl of F is not equal to 0. Around the origin, near the origin, curl of F is equal to 0. Again you see, just looking at the pictures, the curl seems to give you a feeling for this moving, feeling for a rotation. On this point, there seems to be the lines are becoming smaller and smaller, so they are sort of curling around. They are curling around. Here, they are not curling around, they are changing the same way on both sides. And this is really the meaning of curl. Just to quantify this, this could be something like F is equal to, as you increase y, F magnitude increases in x direction. So, this could be a function that is described by this sort of geometric shape. In this case, as you, no matter which way you go on the y direction, F could be y square I. So, let us see if really our feeling about curl is correct or not. If I make it again, in this case I had force field like this, and I wrote F equals y I. Then I also had F equals y square I, and the force field looked something like if I calculate the curl is I j k, partial with respect to x, partial with respect to y, partial with respect to z. This is y, this is 0, 0, and you will see that it has a k component which is non-zero. This gives you minus 1 k. This one, so this is non-zero all the time. On the other hand, in this case, if I take y square, so I j k, partial with respect to x, partial y, partial z, y square 0, 0, it gives me a curl which is equal to 2 y k. I am calculating curl of f. I am calculating curl of f. And this is non-zero for non-zero y, but 0 at y equals 0. So, our feeling that at the origin curl is 0. So, this gives you curl of f is equal to 0 for y equal to 0, but non-zero at any other y for y not equal to 0. Curl of f is not equal to 0. Let me make it clean once more. F equals y I, curl of f as we calculated previously is not equal to 0. F equal to y square I, curl of f is equal to 0 for y equal to 0, not 0 for y not equal to 0. So, you can see that the curl seems to give you a feeling. Here again there is some sort of rotation involved. Here there is no rotation involved. It gives you a feeling for a rotational kind of thing. These quantities, curl and so on, were introduced initially in the studies of fluids. That is where their origin lies. And you can get a feeling, again a physical sort of feeling, if you think in those terms. Think of any given force field, for example, the one that we took, this, or this, or this, or the radial one. And imagine these lines to be representing velocity of a fluid flowing, and take a small matchstick, put it somewhere. So, I take a matchstick, put it somewhere here. If you feel that the matchstick would rotate, then curl is not 0. If you feel the matchstick would not rotate, curl is 0. So, for example, in this case, no matter where you put the matchstick, it will tend to rotate if this is the velocity of the fluid. Curl is non-zero everywhere. In this case, no matter where I put, the velocity is becoming larger and larger as you go outside, the matchstick would tend to rotate. Curl is non-zero. In this case, if I put the matchstick at the center, it is being pushed by the same force on the same velocity on both the sides. It will not rotate. Curl is 0. But if I put it somewhere here, it will tend to rotate like this. Curl is non-zero. In this case, no matter where I put it, it will not rotate. Curl is non-zero. So, this is sort of a physical way of looking at the quantity curl. Having learnt about curl and getting some feel for it, let us talk about it a little more so that you get a better feeling for it. I will first discuss a fantastic theorem about curl that really arises from the way we derived it. So, this is known as Stokes theorem, and what it states is that if I take a closed path and given a force or a vector function f, which I multiply over dl, where dl is a line element along the path, and integrate over this closed path. For example, I could be calculating the force in, sorry, this should be the other way, force in going around this closed path from this point and coming back to the same point. So, I am going this way and coming back to this point, and I want to calculate the work done. Of course, if the force is conservative, that means the curl is 0, the work done is 0. If it is not conservative, curl is non-zero, and this integral is given as the curl of the force field, its perpendicular component to this surface on which the curve is being made, times the area dA. Let me elaborate a little bit. I am taking a closed path. So, I am calculating f dot dl along this path. This is related to the curl. So, I can think of a small area dA on this surface, find the curl there, multiply with the component of curl perpendicular to that surface with that delta area, small area, and add it up. It is a very useful theorem, and you can see right away how curl becomes very important quantity for us. The proof is also very nice, and I would like to go over it so that you sort of get a nice feeling about curl. For proving, I will go back to the way we obtain the quantity curl. The way we obtained was, it was by taking a small rectangular path, going around it, starting from x y, going to x plus delta x y, going up to x plus delta x y plus delta y, coming back to x y plus delta y, and then getting back to where we started from. In that case, we found when I go counterclockwise, then the work done f dot dl along this path, closed path, was equal to delta f y delta x minus delta f or partial f x partial y times delta x delta y, which is nothing but the perpendicular component of f on the x y surface times the small area delta A. Sort of Stokes theorem in a miniature infinitesimal version. Now, what I can do is take a big path and divide it into this small infinitesimal areas, and for each area I can go around like this. For this area I will go like this, for this area I will go like this, and in doing so, finally, when I add f dot dl around each area, you will see that opposite going paths cancel each other, and finally, the only place where they do not cancel is this outside line. So, finally, if I add all these f dot dl's, I am going to get f dot dl around this path. Let me call this C1 to distinguish it from this one. And for each path, I know it is delta f y over delta x minus partial f x over partial y, or perpendicular to of the curl times delta A. So, this is going to be a sum over curl of f perpendicular component times delta x or delta x delta y or delta A, which is nothing but, I can write this in integral form. This is a sum over small infinitesimal areas f times delta A. You have to be careful in these, because we are talking about directional quantities, in that you follow the convention. When I go counterclockwise, and then the thumb, if I curl my fingers around the counterclockwise direction, the thumb gives me the direction along which I should take the component of the curl of f. So, let me rewrite this. What I did was, I took a closed path, divided this into small grids or infinitesimal areas. I took this f dot dl around each path and added it all up. When I added it all up, all these counter going paths cancelled the contribution of f dot dl. Finally, I was left with only this, but the areal integral, that is, so for each small one I had f dot dl, each small one, let me say it C I. When I summed it over, it gave me f dot dl around this path C 1, and this is C I. And when I summed over perpendicular component of f with the area, it gave me integral curl of f perpendicular delta A, and these two are equal, and that is Stokes theorem. Again, I remind you, be careful about the direction. We are talking about directional quantities, and I am going to follow right hand rule. When I fingers curl, right hand fingers curl, thumb gives me the direction along which I should take the component of the curl. As I told you earlier, this Stokes theorem f dot dl is curl of f times delta A integral over that surface really comes from the way we defined initially the curl quantity. So, it is a very useful quantity when I want very useful theorem when I want to see curl in different situations or curl in different coordinate systems. As an example, let me take now what will be the expression for curl in my polar coordinates. Remember, in the beginning of the previous lecture, when I was talking about gradients, I had warned you that when I write gradient as I d by dx, let me just confine myself to 2 dimensions. It does not mean, it does not imply that in polar coordinates it is going to be r d partial with respect to r plus theta partial with respect to theta. In fact, this is not even dimensionally correct. Same thing is true for all other quantities, and as an example, I will just derive curl for you using this definition or this theorem, Stokes theorem, which really initially introduced in an infinitesimal way the quantity curl. So, if I am talking about polar coordinates, I am going to choose my path in polar coordinates as this, following right hand rule. I go counterclockwise. So, for the curl, the component will be coming out of this screen. This point is r theta, this point is r plus delta r theta, this point is r plus delta r theta plus delta theta, and this point is r theta plus delta theta. I will go quickly over this. If I want to calculate f dot dl over this path, it is going to be f r at r delta r, that will be the contribution from this, plus f theta at r. However, as I go out, theta component changes, it changes by partial of f theta by partial of r delta r, and the distance I cover is this one, and this distance is r plus delta r times delta theta. Now, I am coming back. So, this becomes minus f r. However, this is f r at theta plus delta theta. So, this is going to be minus f r at r theta. I should also have theta here, minus how the radial component of f changes with respect to theta, delta theta, and the distance I cover. So, let me make it plus, put the brackets here, delta r, and finally, when I come along this path, is going to be minus f theta at r theta delta theta times r. You can check for yourself, these are the only linear terms. The other terms, if I really look at the other variations of these quantities, they will give me second order terms. So, those are higher order terms, third order terms in delta theta and delta r. So, I am not worrying about those. Now, you can see this will cancel with this, and similarly f theta r delta theta will cancel with this, one part of this. The other part I will get f theta at r theta delta r delta theta. So, let me just write it here, then I will take it over to the next screen. I am going to get this equal to f theta delta r delta theta. The other component f theta r delta theta cancels with this. Then I am going to get plus partial of f theta with respect to r delta r delta theta minus this term will be left, which is partial of f r with respect to theta delta r. So, let me rewrite it. What I have determined is f dl, and this comes out to be, I went along this path, let me copy it, this comes out to be f theta delta r delta theta plus del partial theta partial r delta theta minus partial f r with respect to theta delta r delta theta. This is f dot dl. By definition or by Stokes theorem, this must be equal to curl of f coming out of the screen. This is x, this is y. So, that will be the z component times the area, which is going to be r delta theta times delta r, and that gives me the z component of curl of f in z direction in terms of polar coordinates, and this comes out to be 1 over r f theta plus partial f theta over partial r minus 1 over r partial f theta with respect to partial f r with respect to theta, which in short I can write as 1 over r partial r f theta minus partial f r over partial theta. So, you see, I have been able to derive using the basic definition the curl in a different coordinate system and use the basic theorem of this. This is just to give you a feeling for these quantities. You will obviously be using the advanced version of these or using it more and more in your coming courses in electrodynamics, advanced mechanics, and so on. So, you should practice a lot of problems on this, play around, try to get maybe the other components of curl in cylindrical coordinates or in spherical coordinates. To conclude, I have given of potential energy in 3 dimension, how potential energy and force are related, how we can think of a conservative and non-conservative force, and how we can test them using differential form of differential way of taking curl. And this sort of sums up our introduction and some details of work, energy, potential energy, and so on.